yes, I'll share my slides right now. Sorry. Hold on. Sorry.
Okay.
Okay. Sorry.
So let me introduce our next speaker, Tsang from Ochanomizu University in Tokyo, Japan. And the title of her talk is on Grün's lemma for perfect skew braces.
Thank you for the introduction. Wait. So
Let's start.
yeah. Okay. Yes. Yes. So well, thank you for giving me the opportunity to talk here today. So what my research is on something called skew brace, and very briefly speaking, it's an algebraic structure that came from the study of non-degenerate set-theoretic solutions to the Yang-Baxter equation. So the history is that in order to study the involutive solutions in 2007, Grün introduced braces. But then brace can only cover the involutive solutions. So about 10 years later, brace was generalized to skew braces. And if you consider skew braces, then you can get all solutions, all set-theoretic solutions. So the motivation of studying skew braces, it came from Yang-Baxter equation. For me, I am interested in the algebraic aspect of skew braces. So the motivation is because it has applications to the Yang-Baxter equation, but in this talk, I'm going to focus on the algebraic aspect and just think of skew braces as an algebraic object itself. So what is a brace and skew brace? So first, a brace, well, technically it's a left brace. It's a set, and you want two operations on it. And the requirement is that with respect to the first operation, you get an abelian group. And with respect to the second operation, it can be any group, doesn't have to be abelian. And also you want these two operations to satisfy this compatibility condition. So it kind of looks like the distributive law in a ring, except that you have a minus a in between. And skew brace, or technically skew left brace, is a generalization of brace. And the only difference is that you no longer require the group with respect to the first operation is abelian. You allowed it to be any group. There are certain papers who still write this operation as plus, even though it's not abelian. But in this talk, I'll change the notation to dot when it's not abelian. In this case, the relation here is just in dot operation, it becomes this way, but it's the same relation. Just a remark, when we think of skew brace, there are two groups involved, but using this relation, it's easy to check that the two groups have to share the same identity elements. And here, look, I'm just gonna call it skew brace without left. So here the left comes from the fact that when we look at this relation, we're kind of distributing from the left. So one can define skew right brace similarly, where you do the distribution from the left, from the right. And if both ways, so this is the original distributive law, and if the right version, so you distribute from the right, if the analogous relation holds, then we say that the skew brace is two-sided. Well, just a remark, given a skew brace, whether it's two-sided or not, it actually it reduces to this condition. All the inner automorphism with respect to the second operation is actually a homomorphism with respect to the first operation. So you have this characterization as well. And two-sided skew braces, it's not just the left relation, you have the right relation too, and it makes it a very special family. So most of the skew braces are not two-sided. So let me give some examples. So here is the definition of a brace, and it is known that given a radical ring, one can construct a brace from it. So given a ring, so I'm going to write the addition as plus, and then the multiplication, I'm going to write it as a star. And given a ring, one can define this operation circle by this rule. And it is easy to check that with respect to this operation, you always get a monoid. So meaning that the associative law holds, also has an identity. And the identity is the zero element in the ring, which is obvious. If A is 0, this becomes B. If B is 0, this becomes A. So in general, it's only a monoid. And if you actually get a group, then we say that the ring is radical. So given another remark is that unless A is trivial, otherwise, in order for it to be radical, it cannot be a unital ring. Because if you look at -1, it's not going to have an inverse with respect to this operation. So even though I say ring, really, I mean non-unital ring. So it's well known that if you have a radical ring, then for the first operation in the brace, you use the same operation from the ring. And then for the second operation, the circle, you define it to be this operation. Then it becomes a two-sided brace. So actually, when Grün introduced brace, he introduced it as a generalization of radical rings. So there's actually a one-to-one correspondence between radical rings and two-sided braces. And the correspondence is given by this construction. Given a radical ring, you associate it to this two-sided brace. And given a two-sided brace, one can analogously define a radical ring by reversing the operation here. So brace, one can think of it as a generalization of radical rings. So, and then skew brace is a further generalization of that. So you have the universe of skew brace, and then you have this very special family of two-sided skew braces. And then you also have this family of brace. So brace, if one look back to the definition, a brace is basically a skew brace, and you require the group with respect to the first operation to be abelian. So you have these two very special families of braces, and if you look at the intersection, so these are the two-sided braces. They are exactly the ones that come from radical rings. There's a one-to-one correspondence. And there's another classical way of constructing skew brace, which is from a group. So in order to have a skew brace, it comes with two group operations. So given a group, we can make the group operation that comes with this group to be the first operation in the skew brace. And then for the second operation, one choice is, well, you can just use the same operation. Then obviously it's a group. And if the circle here is the same as dot, it's obvious that both sides gives you ABC. So you get a skew brace. In fact, this is two-sided skew brace. There's another way to construct a skew brace from a group. So the first operation, just the operation of the group. For the second operation, instead of using the same operation, you kind of twist it by using the opposite operation, which is the same group operation, but you reverse the order of multiplication. So in this case, well, obviously, with respect to the opposite operation, you get a group. And for this relation, it's easy to see that both sides you get B, C, A. So given a group, you can construct a skew brace out of it. There are two different ways. But of course, if the group that you started with is abelian, then these two operations are the same, so you're just getting the same skew brace. So the way skew braces that come from this way, essentially they're just groups because you're just using one operation. Here is kind of the one operation. It's just opposites of each other. So because of this, if you have a skew brace where the two group operations are actually the same, then we say that is trivial. And if you have a skew brace where the two operations are opposites of each other, then we say that is almost trivial. So here, trivial doesn't mean that it only has one element, but trivial in the sense that these are basically just groups. So this is a summary of what I just said. So given a group, you can construct a skew brace out of it. There are two different ways. One of them is as a trivial skew brace by using the same operation. Another way is to use the opposite operation, in which case you get an almost trivial skew brace. And if you have an abelian group, then both constructions just give you the same thing. So you have two different ways of identifying a group as a skew brace. And by thinking of this construction, then one can think of skew brace as an extension of groups. It's kind of generalized. It kind of generalizes groups in some sense. And in fact, there are actually a lot of similarities between skew braces and groups. And what I want to do today in this talk is to look at analogs. So there are a lot of similarities. So, and also recently there's a trend to kind of look at how groups are similar to skew braces. Look at ideas, concepts, or theorems in the universe of groups and see whether one can prove an analog of that in the universe of skew braces. So today I'm going to focus on Grün's lemma, which is a well-known result in group theory, which says that if you have a perfect group G, perfect means the commutator subgroup is the same as the group, then you look at the group, the quotient group of G by center, and then you look at the center of this quotient is trivial. This is a well-known result in group theory, and the proof is relatively easy. And I want to look at the analog of this in the setting of skew braces. In order to explain that, first, well, what would be the analog of Grün's lemma? In order to explain that, well, first, if we look at the statement of Grün's lemma, there's perfect groups. So we need to think about, okay, in the setting of skew braces, how do we define perfect? We're also taking the center here, so we need to think about how to define center in this situation of skew braces. There are actually two natural analogs of center. One is called the sulco, and the other is called the annihilator. And also here we're forming a quotient. So we also need to know how we form quotients in skew brace. So once we define these three concepts, then we can naturally ask whether the analog of Grün's lemma is true. So in this case, we look at skew brace. We look at perfect skew brace. I'll define perfect later. And then we want to know, instead of center, we look at the sulco. Or we can also use the annihilator version. So instead of the sulco, we replace the center here by the annihilator. we want to ask, okay, when we take is the circle of the quotient by the circle does it only have one element? And similarly for the annihilator. So what I'm going to do now is explain these three concepts. How do we define these three concepts in the context of skew braces? First, the quotient is not difficult, so let me do that first. So recall that a skew brace, in order to get a skew brace, we need two group operations. And then we also need this relation to hold. So if we think about what substructure that we need in order to form quotient in the case of skew brace. Well, first we need to, with respect to both group operations, we want to form quotient. So we want something that's a normal subgroup with respect to both group operations. But that's not enough. You also want that for any A, when we look at the coset with respect to dot and the coset with respect to A, we want them to coincide. If you have these three conditions, then, well, because it's normal with respect to the dot operation, then we have quotient group. And similarly, for the circle operation, we can also form the quotient group. And the fact that with this third condition, we know that these cosets are actually the same. With respect to dot or respect to circle is the same. So these two are just the same set. So we can form the quotient A modulo I by defining it to be the set of all of these cosets. And the fact that the dot and circle, there is the same coset, is easy to see that when we look at the relation that we need for brace, when we do modulo I is still fine. So then we get then we get a quotient skew brace this way. So these are the conditions that we need in order to form quotients. And in this case, the subset I is said to be an ideal. So this terminology comes from, is analog of a ring, in order the substructure that one needs in order to form quotients. So we're going to call that the ideal. So the quotient, we have defined quotient. Next, we need to define, okay, how do we, yes, is there a question? Okay. So next, then we define what is perfect in the case of skew brace. So remember that for perfect groups, it means that the annihilator, the commutator subgroup coincides with the group G. Then in this case of skew brace, instead of the annihilator, we're going to use this star operation. So given a skew brace, it comes with two group operations, and this star operation is defined this way. So it's a tool to measure the difference between two operations, the two operations dot and circle. I mean, obviously, this is going to be the identity if and only if A dot B is A circle B. So for example, in a trivial skew brace, the dot and the circle coincide, and then what you get is just 1. So this measures how far A dot and A circle B, A dot B and A circle B are different from each other. So let me look at an explicit example. So one of the classical examples of skew braces that introduced is brace that comes from a radical ring. If you have a radical ring, then we can turn it into a two-sided brace by defining the circle operation this way. So in this case, if we compute the star, or instead of dot, we're using plus. So it becomes minus A and then plus A circ B minus B. But then A circ is defined this way. So when you plug it in, the A and B disappears and you just get A star B. So in this special case, the star here is just, it coincides with the multiplication of the ring that we started with. Since this seminar or this conference is called non-associative days, so let me make a remark that for a brace that came from a radical ring, this is the multiplication. Of course, is associative. But for an arbitrary skew brace or even brace, the star operation here is not going to be associative. And that makes things a lot more complicated in the general case. And let me look at another example. So given a group, we can construct a two-sided skew brace out of it. And here I'm going to look at the almost trivial skew brace construction. So here, the circle operation, instead of the same operation, I use the opposite operation. So in this case, when we compute the star, the circle here, we just using the same operation but reverse the order of multiplication. So really, this is just the commutator in terms of the commutator of the group, just the commutator of A inverse and B. So in some sense, the star operation in skew braces is actually an analog of the commutator of a group. So to define an analog of the commutator subgroup, we define, so given any two subsets of A, we can define X star Y to be the subgroup. There are two operations involved, and here we're going to use the first operation. It's the subgroup of the first operation group generated by the elements of this form. In the case of commutator, if you have two subgroups, the commutator of X and Y is the same as the commutator of Y and X at the level of subgroups. But in the case of skew brace in general, it matters which order you multiply. You do the star operation. If you reverse X and Y, you can get a different subgroup. So this star operation is non-commutative on sub-skew braces. So again, in the general case, is quite things are more complicated. So then, if we think of this star as an analog of the commutator, then it's natural to just define the derived ideal of a skew brace to be A star A, kind of the derived subgroup. The derived subgroup is the commutator of A with A, and now the star is an analog of the commutator. So the derived ideal of a skew brace is A star A. It's called the derived ideal, and actually it's known that it's actually an ideal, so it's okay to call it the ideal. Then in the case of skew brace, to define perfect, the natural definition is, we say that a skew brace is perfect if A coincides with its derived ideal. So what I'm trying to say in this picture is that given a group, we saw that we can think of it as skew brace two different ways. One is as a trivial skew brace. One is as an almost trivial skew brace. If we think of it as an almost trivial skew brace, as we saw here, the star is nothing but the commutator. So in this case, the derived ideal, one can convert all the stars to commutators. So in this case, the derived ideal is just the derived subgroup. And so this notion of perfect, so perfect as a skew brace is the same as being perfect as a group. So the two notions coincide naturally. So we have defined quotient. We have also defined perfect. Now we need to define, okay, what is the analog of the center in the setting of skew braces? There are two natural analogs. One is the so-called and one is the annihilator. So let me explain the definition of both of them. So in the case of a group, the center of a group, one way to define is in terms of commutator is a set of elements in a group, so that when you take the commutator with anything, you get the identity. And as we saw earlier, the star operation is an analog of this commutator. So we just replace the commutator by star. So naturally, we define this is a definition of a so-called. It's a so-called of a skew brace A is defined to be the set of elements where, well, not the commutator, but when you do the star operation, you get the identity element for any x in A. And kind of a technical reason, instead of just this, we want to, instead of just this, we also want the condition where you use the commutator. So we want things that are in the center with respect to the first operation. And it is known that the so-called is an ideal. So we can actually form quotient skew brace with respect to the so-called. In the case of a almost trivial skew brace, so where the circle is the opposite operation of the dot. So we saw earlier that the star is just the commutator. So what we get here is the center of the group. So in this sense, the so-called is a natural analog of the center. In the case of group, well, commutator you can do G, the commutator of G and X is identity if and only if the commutator of X and G is identity. The order here, it doesn't matter. You can do either way and you get the same condition. But for skew brace, when you look at the star operation, it matters which way you do the star operation here. It's not true that A star X is 1 if and only if X star is 1. So another way to generalize the center is here we only require A star X. So only one direction. So you can add the other. So you require that you can do A star X, you can do X star A, whichever order you do it, you get the identity. So this is called the annihilator. It's smaller than the so-called. And it's well known that the annihilator is an ideal as well. So we can form a quotient with respect to the annihilator. So we've defined quotient, perfect, and then for analog of the center, we have so-called annihilator. So now we want to look at the analog of Grün's lemma. So the question is, given any perfect skew brace, we want to know if it's true that the so-called of the quotient by the so-called, is it trivial? This question has been studied before, and it's known that the answer is no. But instead of so-called, the annihilator is also an analog, a natural analog of the center. So so kind of based on the paper, it motivated me to look at the annihilator version is that instead of the so-called, if I use annihilator, is it true? So to study this question, instead of stating this way, it's better to state, it's easier to state it in terms of the second annihilator. So just like in the case of groups, one can define the second center. When we look at the annihilator of the quotient skew brace, we can write it as a quotient. So it's something modulo the annihilator of A. Well, in fact, what goes in here is an ideal of A. So I'm going to call this the second annihilator of A. So this condition is just asking whether the second annihilator is the same as the annihilator. So remember that the annihilator is defined to be the set of A that satisfy the three conditions that one wants. Is A star X has to be 1, and also reverse the multiplication order is still 1. And also we want A to be in the center with respect to the dot operation. So we think about it this way. So we basically want to know, given an element in the second annihilator, is it in the annihilator? So does it satisfy all three of these conditions? So then we're reduced to looking at these three equalities. So the first condition corresponds to this. And then the second condition, it corresponds to this condition. And then we also want it to be in the center. So in terms of the annihilator is this. I mean, in general, if you use A, it's not going to be true. So what we want is to look at A star A, the derived ideal. We want to know if it's true. And in the case that A is perfect, then this becomes A. And if all of these three conditions hold, then this is telling us that, well, this is not A star A, but A. So this is telling us that this condition is true. This tells us that this is satisfied. And this tells us that this is satisfied. So in the case that A is perfect, then if all three of these are true, then it tells us that the second annihilator is the same as the annihilator. And in particular, the annihilator here is 1. So there are three conditions to look at. And as it turns out, two of the conditions, the first and the third conditions, always hold. However, the second one, it holds if A is two-sided, but not in general. So this is, in the case of group, where the star operation is just a commutator, if you have this, of course, you can reverse the order and it's still trivial. But in the case of skew brace, that's the problem. In the case of skew brace, you can't just switch them. If you switch them, you can get a different get a different subset. And so it's possible that only this, multiplying them in this order gives you 1, but multiplying them in the other order doesn't give you 1. So in the case of that A is two-sided, all of these hold. And if we look at a perfect skew brace, so these all become 1, then as explained in the previous slide, tells us that the second annihilator is the first annihilator. So then this analog is true. So the Grün's lemma, the skew brace analog, if we restrict to two-sided skew braces, then it is indeed true. In the case that we have an almost trivial skew brace, so an almost trivial skew brace is two-sided, so it coincides. So in this case, we saw that the star operation is just a commutator. So perfect as a skew brace is the same meaning as perfect as a group. And the annihilator here is nothing but the center. So this corollary becomes the usual Grün's lemma. So in this sense, this result is a genuine generalization of Grün's lemma in the setting of skew braces. The only unfortunate part, I think, is that one has to restrict to two-sided skew braces, which is a very special family. So let me briefly say something about the proof of this theorem. So for the first, multiplying the second annihilator and the derived ideal in this order. It's always one. I'm not gonna go, I think that I won't go into details, but you can show that. It relies on this property of the star operation. So in the case of groups, when you look at the annihilator, when you look at the commutator, there's this well-known identity. And replacing the commutator by the star operation, actually the exact same thing holds in the case of skew braces. And making use of this identity, one can show that this is true. And something similar can be used to deal with the commutator condition. And for this one, where we reverse the order of the derived ideal and the second annihilator, the proof of this is actually the same as the proof of this equality, where you have the other order. However, for it to work, we need A to be two-sided, because in the case of a commutator, so the identity that I showed here is the first slot is fixed to be A, and then you do XY in the second slot, and you have this identity. You can also fix the second slot to be A, and you do XY in the first slot, and then you have a similar identity. For this identity, you can replace the commutator by a star, and it holds just fine in any skew brace. And if you look at the computation, how this is proved, the proof is very simple. And one of it relies on the brace relation, the distributive law in the definition of brace. So when you do this computation, you get A circle XY. And then with the definition of brace, you can kind of distribute it and make it, you can replace it by this expression. This is why the calculation works, and you can prove this. However, if we look at the other identity where we fix A in the second slot, if we try to do the same computation, so first, the first line is just the definition of star. And because A is on the right now, what we get is X dot Y circle A. In the case of a two-sided skew brace, then the right distributive law also holds, so we can kind of distribute it and simplify it to this expression. But if in a general skew brace, the right distributive law doesn't hold, so this computation doesn't work. And in fact, the analog of this identity, this is no longer true in a general skew brace. This is why we needed A to be two-sided in order to get this. And then after that, the calculation is similar. Well, I'll skip the details, but in any case, if you assume two-sided, then the computation works out, and you can prove that this is one. But if the skew brace is not two-sided, then actually this doesn't have to be true. So we saw that for the analog of Grün's lemma, or the annihilator version, it's true if we have a two-sided skew brace. But if A is not two-sided, there are counterexamples. It's actually not true. So this is the second result, is that there are actually counterexamples of perfect skew braces A, where when you look at this quotient, is the annihilator of the quotient is not trivial. And by what we by the first main theorem, we know that if a counter example exists, it has to be non-two-sided. If it's two-sided, it's true. So any counter example must be non-two-sided. Also, when we look at this condition, it was reduced to these three separate conditions. And we saw in theorem 1 that two of them always hold. So the obstruction comes from this second condition. So if we want a counterexample, we want this to be not true 1. So it's when you do A and the second annihilator is not 1. So let me just briefly explain how such examples can be constructed. And the construction that I used, it makes use of a semi-direct product of skew braces. So it's a well-known construction in the study of skew braces. Given two skew braces, and also given a homomorphism from, so you want, for C, you want the second operation. And then what we want here, it has to be an automorphism with respect to both of the operations of C. When you have such a group homomorphism, then we can construct a skew brace on the direct product, the Cartesian product of B and C. And for the dot product, you just do the direct product. So in the first coordinate, you use the dot product from B, and then the second coordinate, you use the dot product from C. And then for the second operation, you define it, you use a semi-direct product via this group homomorphism. So here you use the circle instead of the dot. So one can check that if you define dot and circle this way, you can actually get a skew brace. And it's called the semi-direct product of the two skew braces B and C. And it's denoted like this, just like in the case of groups. So to construct counterexamples to the analog of Grün's lemma, instead of arbitrary skew braces, I specialize to the case when B is a trivial brace. So I want both of the operations to be the same. And also I want it to be abelian. So here I'm writing it as plus. And then for C, take it to be a perfect skew brace and also make it things even easier. Assume that the annihilator is trivial. Then in this case, for the semi-direct product that you construct, one can compute the derived ideal and the annihilator explicitly. And it turns out that for the semi-direct product, the derived ideal becomes something like this. And the annihilator is something like this. So really, it just depends on, it's the image. So the derived ideal, it depends on the image of psi minus the identity of B. And then the annihilator depends on the kernel. So really, in this special case, if we want to know so what we want is the counterexample that we want to construct is a perfect skew brace. So we want this to be the entire A. And we also want this condition. So this kind of depends on what the annihilator is. So if we know the annihilator, we can sort of decide whether this is non-trivial or not. So for the derived ideal, we just need to know these images. And for the annihilator, we just need to know these kernels. And the psi here, it ranges over the image of phi. So really, what really matters is these images and these kernels. And the actual what really matters is the image. So what is this image that we take? So can we find a suitable image so that the images or the kernels would do what we want. And in the paper, to make things even easier is to take B to be a vector space. So then looking at these images and all kernels is just a problem in linear algebra. And then what I found, the special case that I looked at is B is this particular vector space. F2 is the finite field on 2 elements, and then look at the 4-dimensional. So I tried to do a 2-dimensional or 3-dimensional, but those are too small and it didn't quite work. So look at 4-dimensional vector space on the finite field on 2 elements, and then see this can be anything. It can be any perfect skew brace with trivial annihilator. Then in this case, when I construct the semi-direct product, what matters is the image. So I found one candidate that would give me these two conditions that I want. The first condition is saying that the skew brace I'm getting is actually perfect. And then this condition tells us that the analog of Grün's lemma doesn't hold. And the candidate of the image that I found is this group in GL4F2, which is isomorphic to S4, the symmetric group on 4 letters. The way I found, I kind of used magma. I was kind of thinking, okay, what kind of conditions I need for these matrices to hold, and then kind of found it using magma. And so here also I found candidates for the image, and I think it shouldn't be too hard to find other choices of the image of phi in order to give you these two conditions. But the one problem is that maybe you can find other choices of the image of phi. But this phi, well, first, the phi here is supposed to be an element of the automorphism group of B. And also, in order to construct this semi-direct product, you need to have a homomorphism from the circle group of C to the automorphism group of B. But here, the C, I'm taking it to, for all the calculation to work, it has to be a perfect skew brace with trivial annihilator. So maybe you can come up with other choices of the image, but maybe you can't find a perfect skew brace with trivial annihilator so that you can actually find a homomorphism with that image. So I think that's one difficulty in the search for this image. I was actually able to find other conditions. Or if you don't require it to be perfect, there are other easier choices of the image as well. But if you want it to be perfect, that kind of makes things difficult. And also, there's also this problem whether there's actually a homomorphism. So meaning that if you find a choice of the image of phi, you need to make sure that there's a perfect skew brace with trivial annihilator, the conditions that we want, so that the circle group of C has a quotient that is isomorphic to our choice of the image. I don't know how, given an image, a possible candidate of image, how easy it is to find a perfect skew brace this way. The way I found it is using the Yang-Baxter package in the GAP program. So my choice of the candidate is isomorphic to S4, and I computed using the small skew brace database in GAP, and it tells me that for at least for these two small skew braces, they're perfect. So, and also they have trivial annihilator, so it's satisfy these. And also the circle group, it has S4 as a quotient. So then one can actually construct this phi. So with this, together with this proposition, it tells us that indeed you can find perfect skew braces for which Grün's lemma, the analog of Grün's lemma, fails to hold. So I think that's all I want to say. Thank you for your attention.
Thank you, Cindy. Thank you very much for your talk. So any questions or comments, please?
May I ask one question?
Yeah,
Yes.
please.
Yeah, okay. So, Cindy, thanks for the talk. So besides the independent statement of Grün's lemma, so what implication it will have on the structure of this skew brace? Like, I mean,
sorry, okay, can you repeat your question?
so if you have annihilator of A mod, annihilator A being trivial, right? So will it have some influence on the structure of this skew brace?
Oh, so kind of the converse. If you assume that this is trivial instead and see what necessary conditions A has to satisfy.
Yeah, maybe it will be.
No, I guess I have not thought about.
Thanks.
Yeah, sorry. Thanks for your question.
Thank you. More questions? So is there a notion of isomorphism between braces? The notion of isomorphism.
Notion of
Yeah. So
yeah, there.
Can we consider the problem whether two braces are isomorphic or not isomorphic? Is it possible to consider this notion of isomorphism?
Yeah, yes. For a brace or skew brace in general, an isomorphism is just a bijection that preserves both of the.
Okay, this is natural, yes. But is it possible to have some classification of such braces or skew braces to classify up to isomorphism?
Classify skew braces that satisfy
So in algebra, for example, we have the classification, for example, in Lie algebras, we have classification of finite dimensional case or other algebras. But in this case, it is something like algebras, yes? We have two operations, but it of course different from the notion of algebra. But since we have the notion of isomorphism, is it possible to try to have some classification of maybe in particular cases?
If not related to this question, then there's attempts to try and classify skew braces of braces up to isomorphism. I think it's a much more difficult thing to do than groups.
But it would be interesting to have more concrete examples of braces. So you mostly give the notion, but what about examples of concrete examples of braces? For example, as matrices or as some finite dimensional spaces?
I think for general construction,
recording in progress.
sorry. I'll return to that.
So this definition, for example, this definition, can you give examples of
I think
concrete?
the classical example, classical examples would be coming from a radical ring or coming from a group. So these constructions, there are other general constructions. For example, if you have a group and you have a factorization, exact factorization, then you can construct a skew brace out of it also.
So you can start with a group and then construct braces, yes?
Yes, the general approach is to fix the dot operation because that's the group. So you fix a group and then you think about how you can define the circle operation.
Okay.
So you get a group and you get this relation.
Using the opposite product, yes? I see. So more questions?
May I ask a question?
Yeah, please.
Yes, thank you for your talk. Related to the last question, I've recently seen a few talks about the relation between the brace structures, skew brace structures, and post groups. I think this is and correspondingly post-Hopf algebras, also in terms of concrete examples. Can you say something about this?
About Hopf groups or what group?
Post groups.
Post. Oh, what are post groups? Sorry.
I think it's essentially equivalent to brace structures. That's what I've understood. But I thought, okay, if you don't know this, I thought recently there were a few talks about the connection between brace, pre-Lie and post-Lie algebras and the corresponding groups as an integration problem.
For Lie algebra,
It's the work by Tsang, Gu, and other people.
Post. Okay, I wasn't aware of post groups. For Lie algebra, I know for skew braces of prime power order, there's some connection with Lie. I forgot the name. Lie rings or maybe not Lie algebras.
I've seen this connection to what's called pre-Lie algebras and post-Lie algebras, which is usually some sort of Lie admissible type of structures that also appear in the context of this factorization. I mean, the factorization problem you mentioned, that you have a group that factorizes into two subgroups in the context of integrable systems.
Oh, okay. Thanks. I did not. I didn't know about this.
Okay.
Thank you.
Okay. More questions? If no, thank you very much for a very interesting talk. I wish you all the best. So we have a 5 minutes break before starting the next talk. Cindy, thank you very much.